I want you to imagine, just for a second, that you are standing on the very edge of the future.
Right. Like right on the precipice.
Exactly. You're looking out at a horizon filled with, humanoid robots quietly folding your laundry in the living room. Or autonomous cars silently navigating city streets at rush hour without a single traffic jam.
Which sounds amazing, obviously.
Yeah, and artificial intelligence systems so advanced they are actively, literally designing their own successors. Now, I want you to ask yourself, what is the single biggest bottleneck stopping that exact future from arriving tomorrow morning?
Most people would probably guess it's the code, right?
Yeah, if you ask someone on the street, they'd say it's the software. They'd tell you, we need better algorithms, smarter neural networks, brilliant new math.
Right. We need the next breakthrough in machine learning.
But what if the real bottleneck isn't the software at all? What if the barrier to the future isn't digital, but entirely physical?
That is a fascinating pivot.
Right. What if the absolute hardest part of building this next era of human history is simply finding enough physical atoms on planet Earth to run the math?
It really requires a profound shift in perspective, doesn't it?
Yeah.
Because we are so conditioned to thinking of technology as this ethereal, weightless thing.
Yeah, we literally call it the cloud.
Exactly. We call it the cloud, but the cloud isn't vapor. The cloud is made of cold, hard metal. It's hyper-refined silicon. It's miles and miles of copper wire and staggering amounts of electricity.
Staggering amounts.
And what we're looking at right now is a scenario where we are rapidly, honestly, violently running out of the physical materials required to support our digital ambitions.
And that physical reality is the exact focus of today's deep dive. We're looking at honestly a fascinating stack of documents today.
Yeah, some really wild stuff in there.
It's a series of detailed blueprints, leaked internal memos, and these bombshell transcripts published on a tech platform called Netizen.
Right.
And all of this material documents an event that just happened yesterday, Sunday, March 22nd, 2026.
It was an announcement that genuinely shook the structural foundations of the technology world. And I don't use the word shook lightly here.
No, that's
This
it.
changes the entire board completely.
So our mission today is to unpack this massive, surprise joint venture announcement. It's a three-way partnership between Tesla, SpaceX, and xAI, and the project is called TERAFAB.
Right. And to really grasp the gravity of TERAFAB, we kind of have to look at the broader context of the tech industry over, say, the last decade.
Okay, set the stage for us.
Well, for years, the AI race was, for all intents and purposes, a software race. You had the titans of Silicon Valley fighting over who had the best researchers.
Right, who had the smartest guys in the room?
Exactly. Who had the most elegant neural network architectures or the most billions of parameters in their large language models.
The software arms race.
Yeah. But this announcement coming out of Austin, Texas, it signals a violent paradigm shift. The race is no longer about who designs the smartest software models.
So what is it about now?
The race is now about who physically manufactures the microscopic silicon real estate that those models live on. It is a massive pivot from the digital ether straight to the atomic grid.
Okay, let's unpack this because the sheer unprecedented scale of what was just announced it's incredibly hard to wrap your head around.
It defies standard tech projections for sure.
Yeah. And to understand the what of TeraFab, we really have to start with the why. Why is a corporate alliance primarily known for, electric cars, neural interfaces, and reusable rockets suddenly deciding to build the world's largest semiconductor factory?
It comes down to an existential math problem, really a brutal supply crisis.
A crisis of atoms.
Exactly. If you look at the raw numbers facing Elon Musk's ecosystem of companies, the projections are frankly terrifying for them.
Let's look at those numbers.
Let's isolate just one single product in their pipeline, okay? The Optimus humanoid robot.
Right, the walking rope.
The leaked internal projections from the Netizen dump suggest that manufacturing Optimus at the scale Musk envisions, and we aren't talking thousands, but millions, eventually billions of units working globally.
Billions of them.
Yeah, that scale will require an installed base of anywhere from 100 to 200 gigawatts of AI compute chips.
Wait, let me stop you right there, because we throw around words like gigawatt, and it completely loses all meaning.
It's a very abstract number for most people.
Right. To put that into perspective for you listening, a single gigawatt is roughly the maximum power capacity of a large commercial nuclear reactor.
Yeah, one reactor.
So when we say 100 to 200 gigawatts, we are talking about needing 100 to 200 nuclear reactors worth of continuous electrical power. Just to turn on the chips for the robots?
Right.
Not to forge the steel, not to build the batteries, just to run their silicon brains.
Precisely. It's just for the logic. And remember, that staggering power draw is just for Optimus.
Oh, right, there's the rest of the companies.
Exactly. Yeah. Now factor in the compute required for the global robotaxi network. Add in the full self-driving inference fleets that are already out on the roads right now.
Millions of cars.
And then add in xAI's massive supercomputer clusters, which are grinding away right now, training the next generation of foundational models.
Right, the training clusters.
When you aggregate all of that silicon demand, it entirely dwarfs the current semiconductor manufacturing capabilities of the entire planet.
Yeah, I was reading through the breakdown of the global supply chain in these documents, and it's like, okay, imagine the entire current global chip supply.
The whole thing.
Yeah, I'm talking about the combined maximum output of fabrication giants like TSMC in Taiwan and Samsung in South Korea.
The absolute titans of the industry.
Right. Imagine their total global output is a garden hose. It's a very high-tech, multi-billion-dollar garden hose, but physically, it's still just a hose.
That's a great way to look at it.
And Musk's projected demand for all these millions of robots and cars and supercomputers, that's an Olympic-sized swimming pool.
Which you're trying to fill with hose.
Exactly. It's not just that the garden hose is running a little too slow. It's that the hose is fundamentally physically incapable of ever filling that pool on the timeline required, even if it runs 247 for the next century.
That analogy hits the nail on the head. The traditional semiconductor foundries simply lack the physical volume capacity to scale to that degree. TSMC, for all its brilliance, is a bottleneck.
A massive bottleneck.
And even if they magically could scale up, relying on them introduces this massive layer of fragility.
How so?
Well, if your entire overarching vision for the future of humanity relies on a third-party supply chain that you do not own, that you do not control, and that fundamentally cannot meet your volume,
Then you're in trouble.
your vision dies on the whiteboard. You become a hostage to someone else's manufacturing queue. You have to wait in line behind Apple and NVIDIA.
Which brings us to the actual blueprints of the TERAFAB solution. And I have to say, looking at these numbers, they go from ambitious to completely staggering.
They are completely off the charts.
The stated goal for this facility being built in Travis County, Austin, is to produce 1 terawatt of AI compute per year. 1 terawatt.
And just for clarity, a terawatt is 1,000 gigawatts, or 1 trillion watts of compute capacity.
So 1,000 nuclear reactors.
Exactly. We are talking about an order of magnitude increase over those already massive 100 gigawatt estimates for the Optimus fleet.
The internal memos from the Netizen leak dig into the specific manufacturing targets, and they are wild. The initial target they are aiming for is 100,000 wafer starts per month.
Which is huge on its own.
Right, and they plan to scale that up to 1 million wafer starts per month. Now, for the listener who might not be a semiconductor engineer, a wafer start is the metric fabs used to measure production.
It's the standard unit of measurement, yeah.
Right. You take a giant 300-millimeter disc of pure crystalline silicon. It basically looks like a super shiny metallic pizza, and you begin the weeks-long process of chemically etching hundreds of little computer chips onto it.
The pizza crust, essentially.
1 million of those metallic pizzas a month.
To properly contextualize that 1 million figure, that represents roughly 70% of TSMC's entire current worldwide output.
70%.
Think about that. TSMC has massive, sprawling fabrication plants all over the globe.
Right.
Infrastructure they have meticulously built up over decades of iteration.
Dozens of fabs.
And TeraFab is proposing to equal 70% of that total global output inside a single, newly constructed site in the United States.
And the end product of all those million wafers, we are talking about spitting out 100 to 200 billion custom AI and memory chips annually?
Billions.
With a B.
That is enough physical compute coming out of a single factory in Texas every single year to rival the entire data center fleets of major industrialized nations.
It is a scale of physical manufacturing that the semiconductor industry has never even modeled on paper, let alone attempted in the real world. You simply cannot find historical precedent for this kind of volume ramp-up in advanced logic chips. But I've got a question about the mechanics of this, because you can't just take a traditional TSMC chip factory, make the building 100 times bigger, and expect it to magically work.
No, absolutely not. The logistics would collapse.
Right. Scaling up a fundamentally slow, intricate process just gives you a giant, slow, intricate process.
Exactly.
So to build this many chips at the speed The blueprints indicate they had to completely rip up and rewrite the rules of how chips are actually made.
And that leads us directly into the architectural layout of the TERAFAB facility itself. To understand why this layout is so revolutionary, we really need to take a hard look at how traditional foundries operate today.
Break it down for us.
In the current paradigm, semiconductor manufacturing is incredibly fragmented. It's completely decentralized. You have one company, say in California, designing the logic processor.
Like an Apple or NVIDIA.
Right. You have another facility, often in Taiwan or South Korea, taking those designs and actually fabricating the silicon wafer.
So the wafers are made across the ocean.
Yeah. Then that incredibly delicate wafer is put on an airplane and shipped to another facility, maybe in Malaysia, to be cut up and attached to memory chips.
It's flying.
And then it might be shipped yet again to an advanced packaging facility to put the final physical casing and interconnects on it so it can actually plug into a motherboard.
It's literally a globe-trotting assembly line. I like to think of it like trying to write and publish a book, right? Where the author is sitting at a desk in New York, the editor is working in an office in London, and the physical printing press is located all the way in Tokyo.
Oh, that's a perfect analogy.
And every time the author wants to change a single comma, they have to send the manuscript via snail mail across the ocean, wait for the editor to approve it, mail it to Tokyo, print a test page, and mail the test page back to New York.
Just to check a single comma.
Yeah. It takes months just to see if the comma looks right.
That global fragmentation introduces massive latency. It creates incredible logistical complexity. And crucially, it heavily restricts how fast you can innovate.
You can't iterate.
Exactly. If you want to try a radically new chip architecture, you have to coordinate across 3 or 4 different global companies, all of whom have their own strict risk tolerances.
Right. Their own lawyers, their own QA department.
Their own proprietary secrets and their own massive production schedules. TeraFab completely detonates that legacy model. They're pursuing absolute vertical integration right down to the atomic level.
The leaked floor plans really highlight this incredible detail. In the Austin facility, mask making, wafer fabrication, and testing will all happen inside a single building.
Under one roof.
It's an end-to-end closed loop. The author, the editor, and the printing press are all sitting at the exact same desk.
And that closed loop is the holy grail of rapid hardware iteration. In the internal documents, they describe it as an incredibly fast recursive loop.
Recursive loop.
Yeah. You design the lithography mask, which is essentially the stencil used to print the nanoscale wires onto the silicon. You make the physical chip, you test the chip, you analyze the thermal and electrical results, and you immediately design the next mask. All under one roof in a matter of days rather than quarters or years.
Which allows for wild physics boundary experiments. Think about it. External foundries would never, ever risk trying a bizarre new material or an unorthodox interconnect layout.
The risk is too high for them.
Exactly. If a crazy experiment fails in a TSMC fab, it ruins a multi-million-dollar production line, it contaminates the clean room, and it delays the chips that Apple or NVIDIA are waiting for.
People lose their jobs over that.
But if you own the entire loop, start to finish, you can fail as fast as you want. But wait, I have to push back here.
Go ahead.
The blueprints specify that they are doing this at a 2-nanometer process node.
Yes, 2 nanometer is the absolute bleeding edge of current physics.
Right. And let's explain what T-nanometer actually means. We are talking about carving transistors into silicon that are so unimaginably tiny, they're only a few dozen atoms wide.
It's microscopic on a level that's hard to fathom.
At that scale, you aren't just dealing with electricity anymore, you are dealing with quantum mechanics. If a barrier is too thin, the electrons just teleport right through it, quantum tunneling, and your chip shorts out.
Which is why the tolerances are so insane.
Exactly. To prevent that, traditionally, your clean rooms have to be pristine. I mean, a single microscopic speck of dead skin or a particle of dust is like a meteor crashing into a city at that scale. It destroys the entire chip.
Totally ruins the wafer.
But the transcripts from the live stream highlight a joke Musk made. He said the TeraFab clean room will actually be dirty enough that you could eat a cheeseburger and smoke a cigar inside.
I remember reading that quote.
How does that make any mechanical sense? You can't just drop a piece of a sesame seed bun onto a 2-nanometer wafer.
What's fascinating here is that the cheeseburger quote, while obviously hyperbolic, is actually a direct philosophical shot at the foundational traditions of the legacy semiconductor industry.
A shot at the old guard.
Yes. Traditional fabs are obsessed with absolute pristine perfection. They move slowly, methodically, utilizing massive filtration systems to ensure their yield rates. The percentage of chips that actually work are as close to 100% as physically possible.
Because they're so expensive.
Exactly, because each wafer is so expensive to make, they cannot afford defects. Musk is signaling a complete and total inversion of that ethos. He is prioritizing sheer volume, speed, and iteration over absolute perfection.
So it's not that they actually want guys in hard hats smoking cigars over the silicon. It's a metaphor for accepting massive margins of error.
Precisely. If your factory is designed to churn out 200 billion chips a year, the economics completely flip. You suddenly don't care if 30 or 40% of the chips fail on the line and have to be thrown away.
You just toss them in the trash.
Yeah. You accept a terrible yield rate as long as the line is moving incredibly fast and you are iterating the underlying design in real time.
That makes sense.
Furthermore, to make a dirty clean room work, you build massive error correction and redundancy directly into the logic of the chip itself.
Software fixing hardware problem.
Exactly. If a speck of dust destroys one core on the chip's internal software immediately reroutes the math to a functioning core. It's the exact same philosophy SpaceX brought to the aerospace industry.
Oh, that's a great comparison.
Right. NASA spent 10 years double-checking math on paper to ensure a rocket never exploded. SpaceX blew up prototype after prototype on the launch pad to learn the physics faster.
And it worked.
It works flawlessly. TERAFAB is applying that move fast and break things hardware ethos to the most delicate, microscopically precise manufacturing process on planet Earth.
Okay, so they've built a massive factory that prioritizes speed and volume over pristine conditions. But if the manufacturing process is this unorthodox, the physical chip they are spitting out at the end of the line can't be a standard, off-the-shelf processor.
No, standard architectures would fail completely.
You can't put a traditional logic chip through this kind of gauntlet and expect it to perform. So what exactly are they building inside this facility? Because the netizen leaks detail two very distinct families of custom silicon, and the engineering behind them is, frankly, fascinating.
The first family of chips detailed in the leak is what we can call the earthly workhorse, or the terrestrial chip.
The terrestrial chip, okay.
This is the silicon designed specifically to be the brain of the Optimus robots and the Tesla vehicle fleet roaming around down here on Earth.
Looking at the specs, there's a very clear lineage happening here. Tesla already has their current AI-4 chips deployed in their cars, right?
Correct.
To bridge the gap while TeraFab is pouring concrete and getting up to speed, they are leaning on TSMC and Samsung to produce a small batch bridge chip called AI-5.
As a stopgap.
Right. And just to highlight how violently fast this technology is compounding, that bridge AI-5 chip already has 40 to 50 times the raw compute power and 9 times the memory bandwidth of today's AI-4.
It is a staggering leap in capability for a single generation. But like you said, AI-5 is fundamentally just a stopgap measure. TeraFab is being built to fully, 100%, take over production for the AI-6 generation and everything that comes after it.
Got it.
And it's important to note the architecture here. The terrestrial chip is heavily optimized for inference.
Let's clarify inference really quickly for you listening. In AI, you have training, which is basically reading the entire internet to teach the brain how to think.
Right, the heavy lifting.
That takes massive supercomputers. And then you have inference, which is taking that already trained brain, putting it inside a robot, and asking it to look at a crumpled shirt and figure out how to fold it in real time.
Exactly. Inference is the application of the knowledge in the physical world. And an inference chip needs specific characteristics.
Like what?
Well, it needs to draw incredibly low amounts of power so it doesn't immediately drain an Optimus robot's battery pack.
Right, you don't want the robot dying after 10 minutes.
Exactly. It needs low latency to make split-second driving decisions in cars, and it needs to be unbelievably cheap to produce, so it can be deployed by the hundreds of millions.
So that's the terrestrial chip. The high-volume, highly efficient brains for the millions of robots walking around our cities and cars driving on our highways.
Yes.
But as impressive as that is, I want to talk about the second family of chips, the absolute star of the show. They call it the D3 chip. Because according to the supply chain breakdown in the leaks, this specific processor is going to consume an astonishing 80% of TeraFab's entire 1 terawatt output.
And the D3 is where the engineering paradigm shifts away from literally everything we know.
It's wild.
The terrestrial chip is built for earthly efficiency and battery life. The D3 is built for an entirely different, incredibly hostile environment, outer space.
Yeah, I was trying to conceptualize how this chip operates, and it's
Yeah.
like, okay, think of the D3 chip as a Formula One race car engine that is intentionally designed by the engineers to run entirely in the red line all the time.
Constantly redlining.
Yes. If you took a D3 chip and put it inside a standard laptop here on Earth, it would instantly overheat, melt through the plastic casing, and catch fire.
Immediately.
It is designed to constantly operate at a baseline temperature that we would consider a catastrophic thermal failure down here. But for its actual intended environment in orbit, it is absolutely perfect.
The thermodynamics behind this are incredibly elegant. If we look closely at the engineering of the D3, we have to ask the fundamental question, why on earth would you purposefully design a piece of delicate silicon to run significantly hotter?
It seems crazy.
It seems entirely counterintuitive to everything we know about computing. But you have to consider the medium it operates in. In the vacuum of outer space, there is zero air.
Right. No air means no fans. If you walk into a Google or Amazon data center down here on Earth, it is deafeningly loud.
Because of the cooling.
Right, because massive fans are constantly blowing freezing cold air over the metal heat sinks on the server racks to keep the chips from melting. You just can't do that in orbit.
Exactly. On Earth, we rely almost entirely on convective cooling, which is the process of transferring heat from a solid object into a fluid medium, like air or water, which then carries the heat away.
Like a breeze on your skin.
Exactly. But in the hard vacuum of space, convective cooling is physically impossible. There's no air to carry the heat. Your only method of rejecting the massive amounts of heat generated by a supercomputer is radiative cooling.
Radiative cooling.
Yes. You have to literally radiate the heat out into the deep freeze of the vacuum as infrared light, using heavy physical metal radiators.
Oh, like on the ISS.
Exactly. If you've ever seen pictures of the International Space Station, those giant white panels sticking out aren't all solar arrays. Many of them are massive radiators pumping ammonia to shed heat.
Wow, okay.
Now, here's the crucial physics equation at play here. The Stefan-Boltzmann law. It states that the amount of heat a radiator can reject scales with the fourth power of its absolute temperature.
Okay, let's translate fourth power into practical terms. What does that actually mean for the chip itself?
It means that the hotter the object is, the exponentially faster it sheds heat into the vacuum of space. It is not a linear relationship, it's a massive curve.
So hotter is actually better for cooling.
Counterintuitively, yes. Therefore, if you engineer a silicon chip that can safely operate at, say, 150 or 200 degrees Celsius without degrading a temperature that would fry normal silicon, you can use a significantly smaller, lighter radiator panel to cool it down.
And when you are dealing with spaceflight, mass is everything. Every single gram costs money and fuel to get out of Earth's gravity well.
Literally worth its weight in gold.
Exactly. A smaller radiator means a significantly lighter satellite. A lighter satellite means dramatically reduced launch mass, which means you can pack way more compute into a single rocket fairing.
The compounding benefits are huge.
So they are designing a chip that runs boiling hot specifically so they don't have to launch giant heavy metal cooling fins into orbit. It's this brilliant cross-disciplinary synthesis of atomic silicon design and orbital mechanics.
It is perhaps the most perfect example of vertical integration crossing traditional industry lines that we've ever seen.
How so?
The semiconductor architects at Tesla and xAI are sitting in the exact same room, talking directly to the propulsion and payload engineers at SpaceX.
Oh, wow.
They're actively optimizing the atomic lattice structure of the silicon itself, specifically to lower the liquid oxygen and methane fuel requirements of the Starship launching it.
That's insane.
You simply do not get that kind of structural synergy if you are OpenAI buying off-the-shelf general-purpose GPUs from a third-party vendor like NVIDIA.
But that brings us to a staggering statistic from the Netizen leak, one that completely reframes this entire deep dive.
The 80% figure.
Yes, let's look at the numbers again. 80% of TERAFAB's output, this massive 1 terawatt megafactory, 80% of it is going to space.
It's unbelievable.
Out of the 200 billion chips produced a year, the vast majority are permanently leaving the planet. Why in the world does Elon Musk need 80% of his total compute capacity floating in orbit?
It sounds like the plot of a sci-fi novel, I know, but it is grounded in brutal, inescapable practical reality. It all comes down to energy constraints, specifically the hard mathematical limit of the Earth's electrical grid.
Okay, so earlier we established TERAFAB's overarching goal, right? An installed base of 1 terawatt of continuous AI compute.
Right.
Let's look at the grid constraint, because the internal memos lay out the math, and it is a complete brick wall. The entire United States electricity grid, and I mean every single coal plant, every wind turbine in Texas, every solar farm in California, every hydroelectric dam, and every nuclear reactor in the country combined, it all tops out at roughly 0.5 terawatts of capacity.
The total electrical capacity of the United States of America is half of what Musk needs just for his AI compute vision alone.
Let that sink in for a second.
Think about that. Earth literally cannot power this operation. If XAI tried to build a 1 terawatt data center in Texas or Nevada, they wouldn't just brown out a city. They would have to turn off the electricity for the entire North American continent just to plug the servers in.
Here's where it gets really interesting, because if the Earth fundamentally cannot provide the power, you only have one option. You have to move the infrastructure to where the energy is limitless.
Exactly.
You have to bypass the grid entirely and move the supercomputers to the sun.
And that is exactly the master plan outlined in these documents. The solution to the terrestrial energy bottleneck is to build massive, autonomous orbital data centers.
But let me stop you, because I did the math on the logistics they propose here, and I almost refused to believe the numbers when I first read them.
The tonnage is mind-boggling.
The netizen sources detail this plan to launch 100 million tons of solar capture and compute infrastructure into orbit per year. 100 million tons.
Per year.
Let's break that down for everyone listening. A fully loaded SpaceX Starship can carry roughly 150 tons of payload to low Earth orbit.
Under ideal conditions.
Right. So to lift 100 million tons, you are talking about roughly 666,000 Starship launches per year. That is a launch every single minute, 24 hours a day, 365 days a year. How does the source material even attempt to justify that level of physical logistics? It sounds literally impossible.
It sounds impossible under the paradigm of legacy aerospace, sure, where a rocket launch is a carefully orchestrated, months-long event.
Right, the Apollo era mindset.
But remember, SpaceX has spent the last decade building Starship specifically as a fully and rapidly reusable heavy lift architecture. They're envisioning a cadence closer to commercial airlines than Apollo missions.
Like planes taking off at JFK.
Exactly. But even if you solve the launch cadence, you hit another massive wall. Who is going to actually assemble 100 million tons of solar panels, radiator fins, and server racks in the vacuum of space?
You can't send astronauts.
No, human astronauts physically cannot do it. The radiation exposure from solar flares, the micrometeorite risks, and the sheer physical labor of building megawatt-class structures are way too extreme for biology.
Which connects the dots perfectly back to the first chip we talked about, the terrestrial chip. You don't send humans. You use the Earth-based Optimus humanoid robots. You launch swarms of them into orbit inside the starships.
Precisely. You have a perfect closed-loop synergy between all three companies in the alliance here. Tesla provides the Optimus robots, which are equipped with the highly efficient AI-5 and AI-6 terrestrial chips, giving them the physical dexterity and autonomous spatial awareness to do construction work.
Space construction workers.
SpaceX provides the Starship launch vehicles and the orbital logistics network to get the mass out of the gravity well. Once they are up there, the swarms of robots assemble these massive, megawatt-class orbital data centers.
And the third piece.
And finally, inside those data centers, you slot in the D3 space-optimized chips from XAI, which are powered directly by pure, unattenuated solar energy from the sun, unbothered by weather, unbothered by clouds, or the Earth's day-night cycle.
It's a planetary-scale supercomputer that doesn't drain a single watt from the U.S. electrical grid. It's entirely self-sustaining.
It's completely independent.
And XAI, which the documents note has quietly been restructured as a SpaceX subsidiary, will use this orbital network to run planetary-scale training clusters. They can beam the data up and down via the Starlink laser network.
Brilliant.
It's a closed-loop ecosystem, not just inside the factory floor in Austin, but in the entire overarching business model.
It is an incredibly elegant architecture that solves the three major bottlenecks of the AI industry simultaneously.
Yeah.
The electrical energy bottleneck, the global semiconductor supply chain bottleneck, and the thermal launch mass bottleneck.
Okay, building an unconstrained, unlimited, off-world supercomputer powered by the sun sounds absolutely amazing if you are Elon Musk.
It does.
But what does this mean for everyone else? What does this mean for the tech giants, the Googles, the Metas, the Amazons, who are stuck relying on Earth's finite electrical resources and renting space on vulnerable terrestrial supply chains?
It sends an absolute shockwave through the competitive and geopolitical landscape. The implications for the rest of the AI industry are nothing short of an existential threat.
Existential.
Yes. This isn't just a new product launch, it's a structural reordering of the entire industry.
Let's break down OpenAI's specific vulnerability first, because looking at the analysis in the leak, they might be the clearest loser in the short to medium term.
They're in a very precarious position.
OpenAI fundamentally is a software company. They build incredible, world-changing large language models. But to actually train and run those models, they rent the compute.
They don't own the chips.
Exactly. They rely entirely on Microsoft Azure's cloud infrastructure, and by extension, they rely on massive clusters of NVIDIA GPUs inside those data centers.
They do not own the base hardware layer. And without that vertical integration, OpenAI is permanently locked into a state of structural dependency.
They're trapped.
They have to pay a massive premium for scarce hardware. They are entirely at the mercy of third-party supply chain delays, and they are rigidly constrained by whatever generalized hardware NVIDIA decides to design.
Right.
They cannot optimize the physical silicon at the atomic level specifically for their exact proprietary software models.
It's like OpenAI is currently renting this incredibly lavish, beautiful, billion-dollar luxury penthouse apartment.
It's a nice place to be.
It's the best apartment in the entire city everyone wants to visit, but at the end of the day, they still have to pay rent to the landlord, and if the landlord decides to double the price or if the power grid goes out in the building, they are completely out of luck.
They can't do anything about it.
Exactly. What Musk just announced with TERAFAB is that he's not renting a penthouse. He is quietly building a self-sustaining sovereign island in the middle of the ocean where he writes his own building codes, manufactures his own bricks, and generates his own unlimited power.
A sovereign AI compute engine. That is the exact specific phrase used in the internal memos to describe TERAFAB.
Wow. Sovereign AI.
Now, if we look across the street at Google, they are in a slightly better position than OpenAI because they do have a history of developing in-house custom silicon. Their tensor processing units, or TPUs, have been doing heavy lifting in their data centers for years.
But the internal analysis points out that even Google's TPUs are structurally disadvantaged compared to what TERAFAB is attempting.
Yes, and it comes back to the manufacturing loop we talked about earlier. While Google designs incredible custom chips, they still outsource the actual physical fabrication to TSMC in Taiwan.
So they're still flying wafers around the world.
Exactly. They are still subject to the exact same global supply chain wait times, the same shipping logistics, and the same fragmented manufacturing process.
And the power constraints.
Furthermore, Google operates a massive commercial cloud business. They have to share that TPU compute across millions of cloud customers, YouTube algorithms, and search queries.
It's diluted.
Right. They do not have a dedicated 1 terawatt facility entirely devoted to a single unified robotics and space ecosystem. Compared to the staggering 1 terawatt scale of TERAFAB, Google's bespoke hardware efforts suddenly look critically underscale.
It really feels like we are reading the obituary for an entire era of the tech industry. For the last 20 years, the dominant, undisputed business model was everyone no lens, TSMC fabs.
That was the golden rule.
Apple, AMD, NVIDIA, Amazon, they all draw up the brilliant blueprints in California, and they email them across the Pacific to Taiwan to be physically built. But TERAFAB fundamentally narrows the defensive moat for everywhere involved in that legacy system.
NVIDIA's moat in particular is a fascinating case study here. NVIDIA retains massive, undisputed dominance in AI training. The initial brute force heavy lifting of teaching a massive AI model how to think.
Right, the H100s, all of that.
But inference, the day-to-day running of that model in a robot walking down the street or a car navigating a roundabout, is where the real physical volume is.
The billions of units.
Custom, vertically integrated application-specific integrated circuits, or ASICs like the Tesla terrestrial chip, are proving to be vastly more efficient and cheaper for those specific inference workloads than a power-hungry, general-purpose NVIDIA GPU.
So NVIDIA loses the inference market.
TERAFAB effectively removes NVIDIA's biggest potential inference customer from the global board entirely.
And then there is the geopolitical calculus here. The analysis in the Netizen leak frames this not just as a corporate pivot, but as a massive strategic maneuver on the global stage.
And we have to look at this objectively. just reporting what the documents outline.
Absolutely. Just parsing the sources here. They point out that currently an overwhelming majority of the world's advanced logic semiconductors are manufactured on the island of Taiwan.
From a purely strategic standpoint, the documents detail how TERAFAB acts as a massive de-risking mechanism for the West against any potential tensions or disruptions in the Taiwan Strait.
Because it's a huge vulnerability.
Right. Any geopolitical incident or blockade there would instantly paralyze the global technology economy. You wouldn't be able to buy a new smartphone, let alone build a supercomputer.
The leaked memos note that Musk explicitly pitched TeraFab to stakeholders as ultimate insurance against geopolitical upheaval. By moving the capacity to manufacture 70% of TSMC's total global output to a single site inside the borders of the United States, it fundamentally shifts the center of gravity for global computational power.
The analysis also touches heavily on the implications for China's domestic tech sector. The documents state that China's internal semiconductor push is currently lagging years behind on advanced 2-nanometer nodes.
And why is that?
This is largely due to strict Western export controls on extreme ultraviolet or EUV lithography machines.
Okay, let's take a quick second to explain what EUV actually is, because it sounds like sci-fi, but it's the core of modern chip making. An EUV machine, made by a Dutch company called ASML, is one of the most complex devices ever built.
It's an engineering marvel.
It literally shoots a microscopic drop of molten tin with a high-powered laser twice while it's falling through a vacuum chamber.
While it's falling.
Yes. The first laser flattens the drop like a pancake, and the second laser vaporizes it into a plasma that emits extreme ultraviolet light.
It's just mind-blowing.
That specific wavelength of light is then bounced off the flattest mirrors ever created by humans to print the tiny 2-nanometer circuits. Because China is blocked from buying these specific machines, they cannot physically print chips small enough to compete at the absolute bleeding edge of AI.
Exactly. And the strategic kicker in the documents is the orbital component.
Right.
If 80% of TeraFab's mind-boggling output is going to be deployed into massive data centers floating in orbit, that compute sits physically beyond the reach of any earthly blockade, tariff, or conventional military conflict.
It creates a scenario of absolute chip abundance that is structurally insulated from terrestrial geopolitics. The netizen analysis suggests this fully validates the core strategy behind the American Ship Yes Act, reshoring critical infrastructure so you aren't reliant on vulnerable shipping lanes.
It's the ultimate reshoring.
Placing the most powerful AI network in human history in a domain where traditional earthly jurisdiction struggles to reach, well, it changes the entire balance of global power.
Okay, so the strategic vision is flawless on paper. A self-sustaining, vertically integrated orbital AI empire that solves the energy crisis and insulates itself from earthly geopolitics.
It sounds perfect.
But the physical, boots-on-the-ground reality of actually pouring the concrete and building this facility in Texas is a whole different beast. And that brings us to the reality check. Is this visionary genius, or is it just the ultimate example of history-making hubris?
We absolutely have to acknowledge the massive elephant in the room, which the leaked documents themselves highlight very clearly. Tesla, as a corporate entity, has zero prior experience running a semiconductor fabrication plant.
None. Zero.
None. Yes, they have brilliant engineers who have designed custom chips, but designing a chip on a computer and physically operating a 2-nanometer foundry are two wildly different things.
Night and day.
Operating a fab at that scale is arguably the most complex, delicate manufacturing process ever devised by human beings.
The risk assessments in the leaks list the sheer cliffs they have to climb, and it is undeniably daunting. First, securing those ASML extreme ultraviolet lithography machines we just talked about.
You can't just buy them online.
No, you can't just log on to Amazon and add an EUV machine to your cart. There are multi-year locked-in wait lists for these tools, and they cost hundreds of millions of dollars each. ASML can only physically build a handful of them every year.
Then there is the human element. The global talent shortage in advanced semiconductor engineering is acute. You can't just take a brilliant software developer from Silicon Valley and ask them to run a chemical etching clean room.
They wouldn't know where to start.
They need thousands of highly specialized, veteran material science engineers, which perfectly explains the incredibly aggressive, almost desperate recruitment funnel we are suddenly seeing pop up on the terafab.ai website.
And we haven't even touched the financials yet. The estimated capital expenditure just to build the physical shell of the facility and outfit it with initial tools is roughly $20 to $25 billion.
That's massive.
And some of the more conservative financial analyst models included in the leak reach $30 to $45 billion to to reach full 1 terawatt scale.
45 billion.
That massive financial burden sits directly on top of Tesla's existing, already massive, $20+ billion in capital expenditures projected for 2026 for their car and battery factories.
Plus, there's the technological risk of the facility itself. Integrating logic fabrication, memory attachment, and advanced packaging entirely under one single roof. The very thing that makes TERAFAB's closed loop so revolutionary is also its single biggest point of catastrophic failure.
Right, because you're mixing environments.
Exactly. Traditional foundries keep those processes separated in different buildings for a reason. They require wildly different chemical environments, different temperatures, and different particulate tolerances. Combining them into one fast-moving line is an absolute engineering nightmare.
Industry veterans quoted in the internal assessments are literally calling this specific task harder than sending rockets to Mars.
And I have to ask, given the historical track record of Musk's companies with massive manufacturing delays, look at how late the Cybertruck was, or the years of struggling to scale up the 4680 battery cells. Is this just pure, unadulterated hubris? Is it physically possible for a car company to pivot to running a 2-nanometer fab essentially overnight and beat TSMC at their own game?
If we connect this to the bigger picture, you have to carefully weigh the legitimate skepticism against the historical track record of achieving the quote-unquote impossible.
Right.
Yes, the timelines are almost always overly optimistic. There are often massive delays. The Cybertruck was years late, absolutely. But look at the macro results. The automotive gigafactories fundamentally revolutionized global electric vehicle mass production. SpaceX successfully built a fully reusable super heavy launch architecture with Starship, when legacy aerospace executives publicly stated the physics wouldn't allow it.
They proved them wrong.
Neuralink is achieving actual functioning breakthroughs in brain-computer interfaces right now. Betting entirely against Musk on a physical engineering problem, no matter how complex, has historically proven to be a highly risky financial and strategic position.
It's the sheer, relentless force of will applied to physical atoms. If even half of this projected terafab capacity actually materializes by the end of the decade, the fundamental landscape of global technology is permanently, irreversibly altered.
It will be a brutal, agonizing execution phase, without a doubt. The engineering burn rate will be immense, but the blueprint is now officially out there, and the capital is in motion.
So we've covered megawatt orbital data centers, the quantum tunneling physics of 2-nanometer lithography, and the massive tectonic shifts in global semiconductor supply chains.
You've covered a lot.
But I want to bring all these massive planetary scale concepts back down to you, the listener. Why should you, going about your daily life, care about an insanely expensive factory being built in Travis County, Texas?
It's a fair question.
You should care, because TERAFAB isn't just about corporate rivalries between OpenAI and Tesla. It is about a fundamental transition in how human beings live. We are moving from a world defined by digital scarcity to a world of absolute, ubiquitous physical abundance.
The silicon atoms being chemically forged in that Austin facility will not be abstract concepts sitting on a server somewhere in the ether.
No.
They will be the tangible physical brains inside the Optimus robot that is standing in your living room, folding your laundry and cooking your dinner.
And making your life easier.
They will be the processors making split-second life-saving decisions in the autonomous car driving your children to school. They will power the massive satellite arrays beaming uncensorable, high-speed data directly to your phone, no matter if you are in downtown Manhattan or the middle of the Sahara Desert.
So what does this all mean?
It means that the foundational rules of the game have changed overnight. As the leaked announcement stated, quantity has a quality all its own.
A quality all its own.
We spent the last 20 years fighting over who controlled the software, who owned the code, who had the most daily active users on their app. The next 20 years of human history will be defined by who controls the physical atoms required to run the intelligence of the future.
The physical layer?
The software race is functionally over. The hardware race has officially begun.
It is a profound realization, and it leaves us with one final, lingering question to ponder long after this audio stops. If 80% of the world's most powerful, transformative AI compute ends up orbiting in space, physically removed from the surface of the Earth, powered entirely by the sun, and operated by a single, vertically integrated corporate alliance who actually governs that network.
It's totally unprecedented.
When the central nervous system of what they are calling a galactic civilization sits high above the legal jurisdiction of any single nation on Earth, floating in the cold vacuum of orbit, who writes the laws? It's a completely blank slate.
It is a new frontier. Not
Yeah.
just a frontier of silicon and rockets, but a frontier of human governance itself.
We started today talking about how the biggest bottleneck to the future was physical atoms, not ideas. It turns out, once you actually solve the atom problem, the ideas you have to grapple with become much, much bigger. Keep questioning, keep exploring, and we'll see you next time.